Welcome, this is Group 7. In this video, we are exploring higher order partial derivatives. We will go over the definition, focusing mainly on the second derivative, its geometrical interpretations, the famous Clairaut's theorem, and some applications. So without further ado, let's dive into the basics. We're already familiar with the concept of the first order partial derivatives and their notations, right? Our second partials are simply derivatives of derivatives. Take the first order results and differentiate them again. Remember, there are pure partials and mixed partials. We've got this cute little flying carpet. If we think of it as a surface, our first order derivatives are just the slopes of those tangent lines. Higher order partials go deeper, showing us the rate at which those slopes change. Think of f sub xx as the mood of our surface in the x direction. A positive value gives us a concave up shape, like a smile. 0 represents a flat inflection point, and a negative value gives us a concave down shape, like a frown. Now for a mixed partial, which measures the twist of the surface, think of it like an arm tilting. A positive value tilts up, 0 stays flat, and a negative value tilts down. Next up is Clairaut's theorem, pronounced Clairaut. It states that for most smooth functions, the order of differentiation doesn't matter. A total lifesaver. To see these derivatives in action, let's look at the wind chill index. Wind chill is the perceived coldness when there is wind. We all know that a windy day feels much colder than the thermometer suggests. Mathematically, we model this perceived coldness as a function of both wind speed and actual temperature. Given the following data table, let's see how we can answer these questions. Let's first recall the formal definition of partials. These limits work perfectly if we have an expression of f. In the real world, we usually do not have an explicit formula. More often, a data table is provided. To handle that, we approximate the partial by looking at the values just above and below our target. Now return to the questions. First, we estimate the first-order partials. We ignore the speed change, focusing on the surrounding wind chill indices. Substitute these data into the equation, and we will get what we want. Now let's estimate the second-order partial derivative, W sub tt. Note that the procedure to find pure partials can be reused, but the difference equations are not the same. The zero partial with respect to temperature says that the air temperature and wind chill are nearly linear. The positive partial with respect to speed says that the wind has a diminishing effect on wind chill, as wind chill declines as speed rises. Now turn our focus on the mixed partials. We estimate W sub Tb by looking at how W sub T changes as speed changes and temperature is kept static. For the reverse partial, we let temperature change while speed is constant. As you can see, these two partials are equal. This tells us that Clairaut was right. Our next model is the heat equation. Heat naturally travels from the surface to the ground. As time passes, those higher order curvatures flatten out until the temperature is even everywhere. This is a beautiful link between time and space. It says that the speed of temperature change is proportional to the second order partial. Now let's see if this heat function satisfies the heat equation by computing the partials. As you can see, the partials are perfectly proportional to each other. Now let's sketch the graph to verify the relation. As you can see, near the surface where x is small, temperature varies greatly and time changes, but deeper, the temperature is more stable. So why do we have this equation? Since heat experiences diffusion during the journey rather than teleports instantly, we get a time lag.
What does the second partial have to do with the changing speed?
That's because of the cosine term with the phase shift that slows down the heating and the exponential term that makes it die out eventually. The final model looks at BMI tracking. To save battery life, the smartwatch uses higher-order approximations to estimate small changes in BMI. Consider the case of Alice in Wonderland. She gained 5 kilograms while losing 10 centimeters of height. We can determine the exact value here. To approximate, take a previous BMI value and add a higher order differential. Let's first use the familiar linear approximation. What about the second order approximation? And the third? As you can see, the higher order approximation we take, the further our result approaches the exact value. And that's a wrap. We have moved from the formal definitions to real-world applications like the wind-chill index and heat equation. As you've seen, higher-order partials are not just extra steps, they are the key to seeing how variables interact and how the world actually curves. Thanks for sticking with us, and happy calculating!